Okay, we're going to calculate the pH of this salt, sodium fluoride. When you're calculating the pH of a salt, you need to consider the cation and the anion. Sodium fluoride has a sodium cation, a fluoride anion. The sodium cation is neutral, so we're going to ignore him. The fluoride anion is basic. We know that because it's the conjugate base of hydrofluoric acid, which is weak. So we're going to treat this like it's a weak base because fluoride ion is a weak base. So we're going to write the base dissociation reaction, which is shown here. Remember that you have a conjugate acid-base pair, one on each side. We're going to put our ice table on here, 3.5 molar fluoride. We're going to ignore water. We have 0 molar HF and OH minus. We're going to add X to the right. We're going to subtract X from the left. We end up with equilibrium values of 3.5 minus X and X and X. We're going to figure out our Kb expression, which is here. We need to calculate Kb from Kw and Ka of hydrofluoric acid, which is given in your table. So when we calculate Kb, that's going to be 10 to the minus 14 divided by 6.8 times 10 to the minus 4, which is the Ka for hydrofluoric acid. And that gives us 1.47 times 10 to the minus 11. We're going to plug in our equilibrium X expressions. We're going to assume X is negligibly small, which reduces 3.5 minus X to 3.5. Then we're going to solve for X, which is the square root of the product of 3.5 times 1.47 times 10 to the minus 11. And that gives me 7.174 times 10 to the minus 6. At this point, you can check your assumption. And 3.5 minus this X value is, when you round it, equal to 3.5. So if we look back, the pH is related to hydrogen ion concentration, but remember that our X is equal to the hydroxide ion concentration, folks. So we're going to start by calculating pOH, which is the negative log of X, which is 5.144. And then we calculate pH. pH is 14 minus that number, which is 8.86. It has two significant figures because all of the original numbers have 2, and then you're going to have 2 digits after the decimal. So 2 digits after the decimal on your pH. Now here we're going to calculate the pH of ammonium chloride. We have to consider both ions again. Ammonium ion is acidic because it's the conjugate acid of a weak base, ammonia. Chloride ion is neutral because it is the conjugate of a strong acid, hydrochloric acid, so it has no tendency to want to recombine with hydrogen ion. So since we have an acidic cation, we're going to treat this like a weak acid. I'm going to write the acid dissociation reaction. NH4 plus dissociates into H plus and NH3. We're going to set up our ice table with 4.9 molar ammonium and 0 molar ammonia and 0 molar hydrogen ion. And we're going to have minus X on the left and plus X on the right. And then we're going to have 4.9 minus X ammonium and X on the right-hand side. We're going to write our Ka expression, which is here. We're going to calculate Ka from the Kb of ammonia. So 10 to the minus 14 divided by 1.8 times 10 to the minus 5 gives me 5.5 times 10 to the minus 10 for the Ka for ammonium. We're going to plug our E algebra expression in. We're going to assume X is negligibly small, which is probably reasonable because Ka is very small, 10 to the minus 10. So we're going to solve for X. X is going to be equal to the square root of 4.9 times 5.5, 55555 times 10 to the minus 10. And we get 5.217 times 10 to the minus 5. We can check our assumption, and it is valid. 4.9 minus this value of X does round to 4.9. Now again, we're looking for pH. Remember that this X in this case is the hydrogen ion concentration, so we can solve directly for pH. pH is the negative log of X, which is 4.28. Again, 2 digits after the decimal because all the numbers you're given have 2 sig figs, so you're going to round it 2 digits after the decimal. We have 4 salts here. We're going to decide if they're acidic, basic, or neutral. We have to consider each cation and anion separately. Sodium is derived from sodium hydroxide, which is strong, therefore sodium is neutral. Fluoride ion is derived from hydrofluoric acid, which is weak, therefore fluoride is basic. So neutral plus basic means this salt is basic overall. Barium nitrate is next. Barium is derived from barium hydroxide, which is a strong base. Therefore, barium ion is neutral. Nitrate is the conjugate of nitric acid, which is also strong. Therefore, nitrate is also neutral. You have a neutral cation and a neutral anion. Those are going to combine to give you a neutral salt. Next, ammonium perchlorate. Ammonium is the conjugate acid of ammonia. Ammonia is a weak base with a Kb. Therefore, ammonium is acidic. Perchlorate is the conjugate base of perchloric acid, which is strong. Therefore, perchlorate ion is completely neutral. It has no tendency to want to combine with H+. Acidic cation and a neutral anion means an acidic salt. Finally, we have a salt that's more complex because we have an acidic cation, NH4. We saw that in part C. And we have a basic anion, fluoride, which we saw in part A. In order to decide if it is acidic, basic, or neutral, we need to calculate Ka and Kb. We're going to compare their relative magnitudes. So the Ka of ammonium, you're going to calculate from the Kb of ammonia. It's 5.5 times 10 minus 10. Kb of fluoride, you're going to calculate from the Ka of hydrofluoric acid. So the Kb of fluoride is 1.5 times 10 minus 11. In this case, Ka is larger than Kb, therefore this salt is acidic because Ka wins, Ka is greater than Kb. Number 3, consider the images below. We're going to figure out which one has the highest pH. So the highest pH is going to be the one with the most hydroxide or the least amount of hydrogen ion. In this case, there is no hydrogen ion shown, it's only hydroxide because that's what's in excess. So we have 3 hydroxides in the X- solution. We have 1 hydroxide in the NaY solution, and we have 2 hydroxides in the Z- solution. Therefore, the one with the highest pH is X-, or NaX. Sodium is just a counter ion here. It's just a spectator ion. Part B, which anion has the strongest base? So in this case, we're just going to see which reaction lies furthest to the right. So we're going to figure out, these boxes represent the equilibrium concentrations. So here, if we count 1, 2, 3, 4, 5, 5, we have 5 X-. We have 1, 2, 3 hydroxide ions, and that means we have 3 HX's. Now, this is at equilibrium. We started out with 8 X-. This was pure X- when we started. That was the initial amount. And 3 of them reacted away. So if we set up a little ice table up here, we started out with 8 initially, 3 reacted, 3 reacted, and that left us with 5. And that formed 3 on the right-hand side. Now if we compare that to Y, we have 1, 2, 3, 4, 5, 6, 7 Y-. We only have 1 hydroxide, that's here, and we have 1 HY. And this also initially started with 8 Y- ions, and then it led to this equilibrium, which means only one of the Y- recombined with a hydrogen ion. So this this base is definitely weaker than X- because only one of them recombined. And so if we do his ice table up here, we initially have 8, we subtract 1, we get 7. For the products, we initially have 0, we add 1, we get 1. So this equilibrium lies further to the left than X-. If we look at Z, we have 1, 2, 3, 4, 5, 6 Z- molecules. We have 1, 2 hydroxides, and we have 1, 2 HZs. So again, this initially started with 8 Z-, and 2 of them reacted away, took a hydrogen ion from water to form hydroxide. So we can write his equilibrium expression here. Originally 8, we subtract 2, we get 6. Again, and then initially 0, we add 2, we get 2. So X- equilibrium lies furthest to the right. So if you look at that one, I'm drawing a red arrow. That one lies furthest to the right. It dissociates the most. Y- lies furthest to the left of these 3. So y minus is the weakest base, x minus is the strongest base. So conceptually, the way you think about that is that x minus is the most associated, lies furthest to the right, therefore it's the strongest base. That's the answer to part B. Another way to answer part B is to just calculate Kb. If we calculate Kb for x minus, then you're going to have 3 molecules times 3 molecules divided by 5. And then Kb for y minus is going to be 1 times 1 divided by 7. And for z minus, you get 2 times 2 divided by 6. So 3 times 3 divided by 5 is 9/5 and 1/7 and 2/3. And the largest Kb is the one for x minus, therefore it is the strongest base. So 2 ways to think about that. Part C, which acid is the strongest acid? The strongest acid is going to be the conjugate acid of the weakest base. So the weakest base we've already decided is y minus because it lies furthest to the left in our base dissociation reaction. Therefore, HY must be the strongest conjugate acid because remember, the stronger an acid, the weaker its conjugate base. The weaker an acid, the stronger its conjugate base. And so they are related to each other through Kw. If one of them is strong, the other one must be weak.